Welcome to this little tutorial on noise-contrastive estimation. In this tutorial, I will explain the motivations behind this technique, how it gets applied in the areas such as NLP, and will show you step-by-step formulation of the loss function and its derivation function as well. This is the symbol used for probability density function for data distribution. One of the main objectives of machine learning is to estimate the data distributions. And we do so by various methodologies, and most of them involve first defining a model of the data distribution and then estimate its parameters. This is the notation I'll be using for the model of the data distribution, that is P with a subscript of theta. We can also say that this represents an estimated or learned PDF. The parameters of the model distribution could either be predicted by the neural networks, or the neural network could directly predict probabilities for a given input. Softmax classification based neural networks are examples of such models that directly predict probability distribution of the input data. Now, whether we are talking about data density function or a model density function, one property that a distribution function or a density function must satisfy is that it should integrate to 1. This property is ensured by the normalizing constant. Let me show you a different way to write the PDF. This shows that there are two components involved. The numerator is called unnormalized PDF. Look at the hat on the p theta. And the denominator is known by various names and is the most difficult thing to tackle. Some of the names given to this denominator are normalizing constant, marginalized evidence, and partition function. I like to call it a troublemaker. If you have watched some of my videos, this problem of normalizing constant appears in Bayesian statistics as well. And the reason is that it translates into an intractable integral when we are in high dimensional realm. And solving high dimensional integrals is not just practical for computers. That said, so far I have only talked about the problem abstractly. Let's see where in practical scenarios we witness a problem of normalizing constant. Here is a simple classification neural network with 4 neurons in its output layers, suggesting that it is assuming 4 classes or categories in which your data can be segregated. The layers in the middle are the hidden layers. This layer is called the logit layer, and its size is also same as that of the number of classes. The neurons in this layer results in what we call logits or scores. The final layer is the softmax layer. It takes the logits and convert the output to the probability distribution. And this is how the softmax function looks like. There is an exponential in the numerator and a normalizing constant in the denominator. Since we want a discrete probability distribution here, we have a summation instead of an integral. And the reason we use exponential function is to satisfy the property that the probability cannot be a negative number, and exponentials have this magical powers to convert negative real numbers to positive real numbers. And the reason we do the normalization part is that probability has to be between 0 and 1, and the elements of a probability distribution should add up to be 1. So far, the normalizing constant is not a problem, at least not a problem for this simple classification network with 4 neurons or 4 classes. But as the number of classes increase, you start to have issues. For example, in an image classification benchmark, you work with 1000 classes. But to be honest, still not a big deal with 1000 classes. So consider a domain of natural language processing. In NLP, one of the tasks is to predict the word when you have set of words in a sentence which we call history. And essentially you make use of these words to make a prediction of the following word, which we call target word. And you can formulate this as a classification problem. That is, you are after the probabilities of the possible words that can fill up this space in the sentence. And you would apply a softmax function and you would choose the one with the highest probability. The problem, however, is that we are talking about words here and the number of classes here will be huge. There is another way, by the way, we formulate NLP problems. This is another setup in which you still have to predict a target word, but you use not only the words that come before it, but the words that surround it. And in most of the time when the problem is formulated like that, we are primarily interested in learning the representations or the embeddings of the word. And in that case, the surrounding words are called context. And this is the word that I'm going to be using as well. This is a term that I will be using instead of history. And here is how you would express this model for predicting the target word given the context. And this time the denominator will be the troublemaker because you have a summation operation, but the number of classes is huge. Now, here I also want to mention that it is not just the fact that there is a summation on huge number of classes. There is also an exponential operation that is happening, and more importantly, because we will be working with log scale, you will be essentially doing log some exponential operation. Other than that, you will still have to take a derivative here, and that taking a derivative of such a large quantity is also going to be not so easy. Now I will talk about how to work around this troublemaker. And I start by introducing you to this paper published in 2010 by Michael Gutman and Dr. Apo from University of Helsinki with the same title as the name of this tutorial of ours, that is Noise-Contrastive Estimation. There are two main insights from this paper that are relevant to our discussion. The first one is the proposal to learn an extra parameter in your neural network that will estimate the z, the normalizing constant. Let me write the target PDF in the form of unnormalized PDF and a normalizing constant. Since we work in a log scale, here is how we would write it. And maybe we can just simply write a number or a symbol called C for log z. This being said, the insight from this paper is not about simply adding an extra parameter to your neural network to predict z, as this had already been thought about before this paper. Rather, the authors are suggesting that if you do this, it would not be that helpful. Because when doing likelihood estimation, the network may make the normalizing constant simply go to 0. And this is why we need to look at something else. This is where the second insight is very important. They argued to solve the problem of intractable denominator by changing the objective function that relies on comparing samples from the distribution and samples from the noise distribution. Noise here means not belonging to the data domain. The subscript n here indicates the noise distribution, and we will be using this symbol in next few screens as well. Since we are comparing between two distributions, it could be seen as a binary classification problem. And when we do binary classification, we use a technique called logistic regression. For the purpose of this tutorial, I am assuming that you have some familiarity with logistic regression, at minimum a high level conceptual understanding. Now, few of the words that have appeared so far, like noise, comparison, discrimination, should be familiar to you, but it is possible that the word contrastive may be new to you. As such, it means more or less the same thing as comparison. In machine learning literature, it is generally used whenever you are comparing two entities, and these two entities could be similar or dissimilar. With these two insights, the authors of the paper showed some exciting results on both synthetic and real data sets. I will not describe them, as I will talk next about how other researchers brought these ideas from this paper and applied to the area of NLP. And then we will construct the objective function based on logistic regression or a binary cross entropy. and explain why it works. So the next paper that really brought the work of Gutman and Dr. Apo to limelight is the one from Henry Min in the year 2012. Their paper was about how to apply noise-contrastive estimation to train language models and work around the limitations of intractable normalizing constant in softmax layer. They conducted various experiments, and interestingly, one of their findings was that normalizing constant did not really matter, or rather, learning the normalizing constant did not matter. They observed that setting C to 1 here, in this case, did not influence the results, and the rationale they gave was that in a more sophisticated networks with relatively large number of free parameters, this information about the normalizing constant can be accommodated by the network anyways. In their paper, they end up specifying the objective function as well. But to be honest, I found it tad bit difficult to follow the steps and the equations the way they laid out, mostly because they did not provide some intermediary steps and jumped and changed context, which made it a little bit difficult to understand, at least for me. So I have made a humble attempt here to build this function step by step so we can see how it is, how the final form came about, and on the way you also end up learning some of the nice tricks that are used. So let's start with the function or a model which is called delta score. This score quantifies the relationship between the input and its context. Inputs to this function are the target word and its context. The W with the subscript plus is indicating that it is from data distribution. And C, of course, here is for the context. This score is sort of equivalent to the logits that we saw in the classification layer. Now we take this score and apply the sigmoid nonlinearity to it. In neural networks, we say that we are applying sigmoid activation function, which would convert the score to the probability. That is a number between 0 and 1. And as is the convention, we generally work at log scale. So essentially, we are interested in getting log prob. And this is just the first aspect of our objective function where we would want to have this term optimized. Quite like this, we add the second component, which is about the compatibility between the samples from the noise distribution and the context. This essentially is a logistic regression or a binary cross entropy loss function written in a little different way. And the difference is stemming from the fact that in the papers and their experiments came to the conclusion that unlike traditional logistic regression where you are comparing a positive sample to a negative sample, here it would be wise to have more than one negative samples per positive sample. So we say that we have, for each positive sample, we are dealing with k negative samples. And this is the noise contrastive estimation loss function in its simplest, as well as the practical form in which it is implemented. We now look at the delta score function or the model in a bit more detail. Since we are talking about logistic regression, it is but natural to see our score function as log odds ratio. Again, if you do not know odds ratio, it would be difficult to appreciate this. I would recommend doing a Google search on how probabilities and odds ratio are related to each other, and you would find many excellent resources. For us, there is one difference though from the traditional log odds ratio, and it is because we are considering that the samples from the noise distribution are k times more likely, and hence it has an influence on how we have written our log odds ratio. Notice in the denominator there is k times the distribution. The same story is for the delta score for the negative samples. We apply the sigmoid function on the delta score, it would look like this. So let's put the value of the delta score. Now I have flipped the ratio and thereby removed the negative sign in the exponential function. Since exponential and log cancel each other, we get this expression, and this is the final simplification of this. As such, in many papers, the authors started with this expression and called it the posterior probability of positive samples. Similar simplification when done on the delta score for negative samples results in the expression shown on the right side of the screen. Steps are same as I described for the positive samples. And therefore now we can write our loss function where the delta scores are substituted with these expressions. As you can see that the model distribution, that is p theta, is still intractable because of the normalizing constant. And so given the insight from Min et al. That we can replace p theta with its unnormalized form. But from a notation point of view, we still keep it as it is so that the expression is general enough for situations where we may be interested in computing the normalizing constant. Now, this is fine and dandy, and we can stop here. When implementing it, you do not even have to go to this step as such. Just limit yourself to score function where the score values are given by the neural network. But how do we know that this arrangement or this new objective function is capable of doing what we want, or at least what our softmax based classification network was doing? Well, one simple answer when you come up with a new objective function is to maybe just experiment it by training many different neural networks and see how they perform. And I don't see anything wrong with that. It's a legit approach. However, it would still be interesting to see or prove mathematically that indeed this objective function will work. And to do that, we need to look at how the gradients of these objective functions are calculated or how they look like. And maybe there is a secret hidden in there which is telling us that this is a legit objective function which is as capable as that of the softmax based classification. I want to emphasize again, you don't have to do any of this because your auto differentiation library like TensorFlow or PyTorch or JAX, whichever is the new flavor, it will take care of it for you. In the next few screens, I will show you some derivations and simplifications to prove that this objective function is indeed a valid, legit objective function. And the first step here is to simply differentiate, because we are interested in getting the gradient of our loss function. So we are just doing a differentiation with respect to theta. Theta is the set of parameters of your model. And here I have simply converted the log of fraction to the log of subtraction operations. I have moved the differentiation inside the sum operation. It is a legit thing to do. Now, due to the lack of space, I'm going to simplify these two components separately, and this is why I have labeled it. So the first one is component 1, second one is component 2 inside the summation, and then whatever we will do for component 2 will apply to all the k negative samples. Here I have rewritten the first component. Now moving the derivative symbol inside the expression. So this is where we will apply an identity to our expression. The identity is shown in orange and is about the dual representation of derivative of a log of a function. Essentially, it ends up removing the log. So after applying the identity, our expression is going to look like this. Take a moment, as it is quite big, which makes it difficult to parse through. Now, another thing to note here is that the second term in this expression is a constant with respect to theta. So we can remove it. We now use one more identity to simplify the expression. This identity is also about the relationship between logs and derivatives. And after applying this identity, our expression would look like this. Essentially, this was a trick to get the derivative of a log to be extracted out of the expression, as you can see in this next simplification. And the final simplification looks like this. For the component 2, the steps are more or less the same. You are going to use these two same identities to come to this simplified expression. And now we can have this final expression for the derivative of our loss function. Now we make this assumption that k is a very large number. We would actually say that k approaches infinity, and when it does so, we can see that the second term will approach 0 because there is a k in the denominator. Look in the rectangle here. K is in the denominator, so if it goes big or towards infinity, this term will become 0, essentially eliminating the entire component 2 from this expression. On the other hand, the coefficient in the first term will approach 1 as we have k both in the numerator and in the denominator. And because of this, gradient is same as that of log likelihood gradient. This is the proof that this formulation of the objective function based on the logistic regression should work. Now, do we really use infinitely number of noise samples? I don't think so. You know the answer already. So this is why these kind of proofs are called asymptotic proofs. And so really the trick would be that how many noise samples would be good enough for our problems. And this is the expression which is also listed in the seminal paper from Andrew Min, the paper that I talked about earlier. And you will find this expression of the derivative of the loss function in there. Interestingly, the next year, that is 2013, Min published another paper at NeurIPS conference in which the focus is on learning embeddings efficiently using noise-contrastive estimation. This paper is very similar in spirit to the previous one, focusing and explaining the details of experiments and the usage of noise-contrastive estimation as the remedy. However, here the expression of the derivative of a loss function was provided in this form. Now, this expression and the previous ones are really the same. Here I show you the proof in few steps that the expressions that are mentioned in 2012 and 2013 papers of Andrew Min are really the same. And for that, I take the help of something that we had worked out, derived earlier, which was the sigmoid of the delta score function. And if I take 1 minus sigmoid of delta score function, I will end up with this expression, which is the one that was used in 2012 version of the derivative of the loss function. So point being that they are the same thing. And this brings us to the end of this tutorial. So far I have explained noise contrastive estimation with NLP as an example, but the same technique is now being applied to do representation learning on images. Generally, the images are broken down into patches and augmented to create what we call positive and negative pairs. A famous self-supervised learning technique in computer vision is called SimCLR, which uses the concept of noise contrastive estimation. And that is all for today. I hope I was able to convey the insights behind this concept as well as help clarify the various derivations, expressions, and the equations. With that, I thank you for the precious time you have spent here. Good luck with your learnings and see you next time. Bye-bye.